Welcome everyone. Today we are very happy to have Gunnar König speaking. He's a postdoc with Ulrike von Luxburg at the University of Tübingen, and he's known for both his critical look at explainability, interpretability, and also his constructive ideas. And today I think is about a new method, so it's on the constructive new ideas side. So I'm very eager to hear. Thanks, Gunnar. Go right ahead.
Yes, thank you for the introduction. So yeah, as you said, I think we're trying to be constructive in this work. It's called disentangling interactions and dependencies in feature attribution, and it is joint work with Erik Günther and Ulrike von Luxburg. So what is it about? And I'll start very informally with an intuitive example. So suppose that you are a scientist who uses machine learning and in combination with feature attribution to learn something about the data generating process. So this is a very common thing now if you open a science paper that people use machine learning and then combine it with some feature attribution. In this specific illustrative setting, we try to predict the price of a house and have just three features: longitude, latitude, and ocean proximity. And now we would get a plot like this. At this point, it doesn't really matter how exactly these scores are defined. What's important is that we would get one score for every feature that aims to capture somehow how relevant the different features are for the target. And in our talk, we will specifically attribute the model's performance. I'll talk about how exactly these things are defined a bit later on. But yeah, we have one score per feature. However, in typical real-world scenarios, the performance is not only the result of individual contributions, but also the result of cooperations between features. And in this specific setting, because we can make sense of the variables, so we know what longitude, latitude, etc. are, we can already hypothesize about different cooperations that could be going. So for instance, longitude and latitude, we would suppose to be not as predictive as alone as they are together, because via a statistical interaction, meaning that one variable can modify the effect of another variable, we get much more predictive. Or in plain English, if we know longitude and latitude together, we can locate a property in a specific neighborhood. And this is something that is very informative of the price of a house. And another cooperative force that we might hypothesize being present here are dependencies. So in this plot, we see that ocean proximity receives a very little score, which is curious because at least I would pay much more for a house that is close to the ocean. And yeah, we would hypothesize that what's going on here is that ocean proximity is simply redundant with the remaining features. So longitude and latitude explain away the contribution of ocean proximity. Yeah, so the point here is we have these scores that explain the relevance in terms of the individual features, but we have contributions that stem from groups of features and their interplay. Now, this conflict, I would say, is one of the central debates, or has been one of the central debates always in feature attribution. And the mainstream approach of solving this has been to argue what the best or the fairest way is to attribute these cooperative features to the individual, and these cooperative contributions to the individual features. And I think the most prominent example here are Shapley values, which essentially divide cooperative features fairly among the partaking features. In some settings, this may be what we want, but this always conflates individual and cooperative contributions. And in many settings, in my view, this misses the point. So if we think about practitioners, again, who want to learn something about the data generating process, very often they care a lot about cooperations. So for instance, doctors really care about interactions with the treatment. So keywords here are prognostic versus predictive variables. And they want to know whether variables become more predictive when combined with other variables via dependencies. The keyword here is suppression. Also, even if we regard this purely from the standpoint of interpretation, it is clear that cooperations are an interesting information, because if we know that a variable is also relevant due to a cooperation between features, that means that to really understand why this feature is relevant, we need to interpret it in combination with other variables. And this is something that we don't get by like the standard feature attribution method. So what do we do about this, or what do we suggest to do about this problem of like this old typical feature attribution, which conflates these different types of contribution? We try to disentangle them in the scores. And yeah, in the rest of the talk, I will explain how exactly these different plots are computed. But for now, the important thing is the score that we see here on the left is decomposed as the sum of cooperative and individual contributions. So this black horizontal bar here is the score that we see here on the left. And then we have these different bars where the magnitude corresponds to the size corresponds to the magnitude of the contribution, and the direction corresponds to the sign. So here, for instance, for ocean proximity, we would see that there is a large standalone contribution, but due to a negative contribution of the dependencies, in plain English, the feature is redundant with the remaining features, the local score is low. Or for longitude and latitude, we see that interactions are quite important. And yeah, one reason why Loco considers this feature to be important. Okay, this is the high-level idea. Instead of trying to somehow force everything into one score per feature, we try to make these different individual and cooperative contributions explicit. Now, first, so later I will explain the dip decomposition, which is our main contribution, but for now I will explain how this plot is generated. The method here is called Loco, and Loco is an example of a global loss-based feature attribution technique. So global loss-based feature attribution is not sharp lime counterfactual integrated gradients. I don't talk about all of these methods today, although this problem of cooperative versus individual contributions, of course, is a thing there too. But when we are interested in learning something about the data generating process, these global loss-based feature attribution methods are particularly interesting because they can be related to the data generating process, as we will see in a bit. And they are also very popular in this context. So what do we mean by global loss-based? By global, we mean that we do not explain one specific observation, but rather we try to explain the relevance of variables over the whole data set. So instead of answering which feature is relevant for the specific prediction, we ask which feature is relevant for predicting accurately in this data set. And loss space means that we do not try to reconstruct the or like explain the mechanism of the model. We do not try to explain the prediction, but rather we try to capture how informative the features are for the target, and therefore we attribute the model's performance, so something like the R-squared, the accuracy of the model, so to speak, to the individual features. Again, in this class of explainability methods, there are many, many different methods, SAGE, PFI, CFI, etc., PP. For this talk, we focus on one that is particularly simple. It's called Loco. Loco stands for leave one covered out, and this is the method that we have also seen in the beginning already in this plot. Intuitively, it measures, as the name kind of says, how much the risk increases if we remove a variable from the model. The intuition here is, if removing a variable from the model doesn't change the performance a lot, it cannot be important. But if removing a variable changes the risk a lot, of course, it should probably contain a lot of relevant information. To make this a bit more formal, first some very basic notation. So X are the features, Y is the label, and P is the distribution in which our features live. We often talk about sets of features, and the set of all features we denote as D. And yeah, it's simply the indices of the different features. Then we have the machine learning model F, we have the loss L, and the risk R. Now, Loco reasons about or like quantifies how much removing a feature changes the risk, and therefore we need a way of removing variables from the model. And yeah, this is also one of the big debates in the field. Loco solves this in a very easy way. To get a model that only depends on the set of features S, it simply refits the model on the subset of features. We could also obtain this in different ways, but now let's suppose that we simply refit the model on a subset of the features. And then to quantify how much the set of features contributes, or how much kind of value the set of features has for predicting the target, we now quantify how much the risk decreases if we add these features to the model. So here, this F of empty set would be the best constant model. So the mean, for instance, of the outcome in a regression setting. And now we add the set of features S to the model and see how much the risk decreases. And this is the value of these features. This definition will pop up, or like the value function will pop up many times over the course of the talk. So be sure to really memorize this, because otherwise it will be hard to follow. And yeah, we can, among others, use this value function to define or introduce Loco. And more specifically, Loco, as kind of the name already tells us, measures how much the value increases, or let's say how much the value decreases if we remove one variable. So the value function for all features versus the value function for all but one features. And this gives us one score per feature if we do this for every variable, and then we get a plot like this, which captures this relevance. Okay, so this is the formal definition. I already mentioned that a nice thing about Loco, or more generally global loss-based feature importance, is that it can be related to the properties of the data generating process. And in the case of Loco, the interpretation in terms of the data generating process is also very simple. And yeah, I guess this is very relevant in this setting. So if we have L2 loss and optimal models, we can easily show that these models and restricted models correspond to conditional expectations, a property of the data generating process, that the value function corresponds to the explained variance of Y given the subset of features. So how much variance of Y can we explain using the set of features? Also a property of the underlying distribution. And Loco would be how much more variance in Y we can explain if we add this one feature to the remaining features. So this gives us the link between this feature importance and properties of the data. Okay, so much about this plot. Now we understood kind of how this plot is computed and what it means for the data generating process. But now let's come back to the main story, and let's recall that although this already has quite a nice interpretation in a sense, it still conflates these individual and cooperative contributions. And the goal now is that we want to make explicit for Loco which part of the score stems from individual and which part stems from cooperative contributions. The first naive idea would be to simply take this Loco score and decompose it as the sum of the individual contribution. This would be simply given by computing this value function for one feature alone. So how good is our risk in a sense if we only have one feature available? And then defining the rest as everything that is the result of cooperation. And by simple reformulation, we already get that this cooperative impact, as we call it, has a very intuitive form, and it seems to make sense. It is the difference between the joint contribution and the sum of the individual contributions. And here the individual contributions would be the sum of our feature of interest plus the sum of the remaining features. So far, so good. Everything seems fine for now. We have separated this individual contribution and kind of the effect of cooperations on this local score. But this, the title already gives it away, right? It's a naive approach. This does not allow us to expose whether there is, or to reveal whether a cooperation was relevant or not. To see this, let's look at the following simple example. In this example, this example is constructed in a way such that we have both cooperation via interactions that is relevant and also cooperation via dependencies that is relevant, but both cancel each other out and therefore they are not visible. So let's first look at the left side here. Y is defined as the sum of x1 and x2 plus some interaction term, meaning that to optimally predict y, we need this interaction. We need a cooperation between the variables in terms of x1 and x2. And also really to understand what they mean for the target, we need to look at them jointly, right? And at the same time, we have a dependency in the data that makes the variables partly redundant. So we have a positive correlation, so they contain similar variation. So at least partially they can replace each other. And in this specific setting, the values are chosen such that they exactly cancel out. Yeah. So the joint contribution in this setting is simply the sum of the individual contribution, and this cooperative impact is 0. So we directly see that this cooperative impact is not enough. Moreover, this example shows that these value functions, which are the basis of all these feature importance methods, do not allow to disentangle the different cooperative contributions and therefore do not allow to reveal whether a cooperation is present. Why? So in this setting here, all possible, so if we have only just features, all possible value functions are exactly these three. And we compute all of them, and just by looking at them, there's no way of seeing that we have this strong interaction and that we have this dependency. So the kind of intermediate conclusion here would be to reveal whether cooperation is relevant for the predictive performance. We need to decompose this cooperative impact into the contributions of interactions and dependencies. We have to kind of separate them. And the main idea here is to decompose the model to be able to decompose this cooperative impact. So again, we recall these value functions alone do not allow us to separate these individual and cooperative contributions. But if we had a model where we had a separation between a part where cooperations between via interactions cannot be there, so the main effects, there can be no interactions, and a part where they are allowed, then this would potentially allow us to cleanly decompose this cooperative impact. However, just saying we want to decompose the model into these two parts doesn't really allow us to do this yet, because first of all, simply saying we want to decompose the model in this form isn't unique. We could simply say H is equal to F, right? So we need another constraint to make this unique and also meaningful. Furthermore, we want this to be easy to estimate, and also the decomposition needs further properties such that in the end we get a clean separation of the cooperative impact. And inspired from work in functional decomposition, we introduced this further constraint by defining a pure interaction as follows. So we do not only want to separate main effects and interactions, but we also want this interaction component to be pure. By pure, we mean that everything that can be explained without an interaction should be explained without an interaction. And more formally, we can do this by saying we approximate f using a additive model G, and then we take the difference. And this residual, all of the variance that we cannot, everything that we cannot explain using this additive model is given by this pure interaction here. And we can show that this has some nice properties. So first of all, it's unique. Secondly, it's very easy to estimate. So at least in the tabular setting that we assume here, there are many powerful generalized additive model classes out there based on boosting machines, etc., pp, which allow us to easily estimate this and then also the pure interaction. And because of the way it's defined, it satisfies some nice properties. So the additive model components and the pure interactions are orthogonal, and also like the pure interaction and all the individual features are orthogonal. And this will be super important for the decomposition in the end, because many terms cancel out as a result of this property. Furthermore, we can show that also the main effects are in theory unique up to a constant under mild assumptions about the density. And taken together, this will allow us to clearly decompose this cooperative impact into the contributions of pure interactions and main effects. So how does this decomposition look like? This is the kind of main result. So given that we have a optimal model F and we have main effects given by G, so this we assume here for this result that these main effects are optimal. So this is the best approximation of F using a additive model. And given the corresponding residual, this pure interaction, then we can rewrite this cooperative impact, which you remember was the difference between the joint contribution and the sum of individual contributions, as the interaction surplus, a term that only depends on the pure interactions, and the main effect dependencies, a term that only depends on the main effects and vanishes when the features are independent. More specifically, the interaction surplus is given simply by the variance of the pure interaction term. So this is the variance in y that we can only explain with the interaction. And the dependencies, again, is a term that vanishes when the features are dependent. So we have some independent. So we have these explained variances here, which I won't go too much into the details here, but in essence, these terms capture how much of the variance of one GAM component could also be explained by the respective set of other features. So this measures somehow the redundancy between the two groups of features. And then we have a covariance term, which captures whether the two main effects work in the same direction or rather cancel each other out. I will say one more thing about this term. It can be positive or negative. So it's clear that the interactions are always positive. So the contribution that we can only unlock more performance as a result. Oh, sorry, I skipped the slide. If we allow for actions. But dependencies can both induce a redundancy, but also unlock more predictive performance. And this is also captured in this covariance. To make this a bit more intuitive, let us look at a concrete example. So here we have a positive cooperation via the dependencies. And in this little illustrative example, we suppose that we are trying to predict the grade in an exam using two features. On the one hand, whether a student did their homework, and on the other hand, whether a student attended the review session. Now, in this setting, so we'll walk through this step by step, don't worry. we first assume that there is a negative correlation between the two features. This is visualized here. So, and the intuition is that when a student did their homework, the student is more likely to skip the review session and vice versa. If the student didn't do their homework, they are more likely to go to the review instead. Also, both variables have a positive effect on the outcome. So both doing your homework and attending the review session probably gives you a better grade. However, if we only observe one of the features, their effects cancel out at least partially. So if you observe that somebody attended the review session, that is good on the one hand, because that means that the student probably learned something in the review session, but it also makes it more likely that the person didn't do their homework. And therefore, these two effects cancel out. So both have in the model a positive effect, but via the negative dependencies, they cancel each other out partially. However, if we observe them both, their respective positive effect is revealed, and suddenly the predictive performance is increased. So for instance, feature X2 in this example is not predictive at all. It is independent of the target. So if you compute this model F2, it is simply a constant. However, when combined with X1, it suddenly becomes more predictive. And this is what we also see in this dip decomposition here. So the contribution of feature X2 is 0. We don't see it here. The individual contribution of feature X1 is positive. This is this bar. And then we also have this positive surplus stemming from the dependencies. Okay, so much about the dip decomposition and the theory. Now let's look at some examples. Before that, let us recall for a second how the dip decomposition was defined and how this relates to loco. We recall that loco was defined as this difference in the value function for all features minus the value function for all but one features. And we rewrote this as the sum of the individual contribution plus this cooperative impact. Over the last couple of slides, we showed that we can decompose this cooperative impact as one term that only depends on interactions and one term that only depends on dependencies between the main effects. Now, if we visualize this again, so we have this black bar being the loco score, then we have this gray bar being the individual contribution of this one feature. We have the purple one being the main effect dependency term and the green one being the interaction term. Then we can already see quite a few things in the data. Also some more details. So the scores are local scores. We use L2 loss, and to obtain this pure interaction, we use a so-called explainable boosting machine. And so the first thing that we observe is that in this data set, interactions do not play a large role. However, we observe this phenomenon that I also illustrated with this example about the homework. And this actually occurs quite often, that residual sugar becomes more predictive, not because of interactions, but because of dependencies. And the intuition here is, if you also look at the pairwise relations, etc., you find that density and residual sugar are positively correlated. So adding more sugar makes a wine more dense, but they have opposing effects on the wine quality, which we're trying to predict here. And therefore, their effects partially cancel each other out unless both are looked at the same time. Another setting would be the California housing data set, which we saw in the beginning. Again, we decompose loco with L2 loss and look at we fitted the generalized additive model using explainable boosting machines. And here we see that interactions contribute to the scores for longitude and latitude. And again, we see that ocean proximity receives a low score, although it has a large standalone contribution because it is redundant with the remaining features. Okay, so these were the examples. There is some related work that goes in a similar direction. Most notably, there is an emerging literature on explaining interactions. So Shapley interaction values, for instance, and higher order variants. So my colleague Sebastian Bort, together with Ulrike, has this very nice paper about showing how Shapley values can be seen as a form of functional decomposition in a way, or like can be better understood through the perspective of functional decompositions. However, the problem with all of these approaches is that they focus on explaining the mechanism of a specific model versus explaining the data. So they are not really useful for somebody in science who tries to better understand a specific data generating process. And secondly, they neglect the role of dependencies. And I hope that I could convince you over the course of this talk with the examples that we've seen that they are super important to really understand the cooperative structure. Super important to understand whether variables must be jointly or can be interpreted separately. There's also some work in functional decomposition which tries to separate pure interactions and main effects. However, they are typically infeasible to estimate. So the closest thing is generalized ANOVA, and it tries to decompose a function by allowing for all possible subgroups of variables and ensuring that they are all hierarchically orthogonal, and this is very, very difficult to estimate. There's also some literature in information theory about decomposing the mutual information. Here the goal is to decompose something into standalone, redundant, and synergetic components, but it's a concern with mutual information where we care about regression, and also doesn't disentangle these two different qualities of cooperation. So interactions are a stronger form of cooperation than dependencies, because there we do not only have to interpret variables jointly, but also have to take the respective values of the other features into account. And then there's commonality analysis, which focuses only on linear models. So in summary, what did we do? We proposed a general way of decomposing global loss-based feature attribution into standalone individual contributions and cooperative contributions. More specifically, in order to do this, we show that we have to disentangle cooperative contributions stemming from interactions and cooperative contributions stemming from dependencies. We also argued that this is super important for practitioners because they want to know about interactions and dependencies. And it's also relevant because it tells us whether features must be interpreted jointly. Furthermore, we showed that our decomposition is unique and easy to estimate. And there's also a Python implementation. Now the elephant in the room is kind of, we now focus on decomposing these feature importance scores, and there we always have these two groups that we compare. We always have these comparisons of value functions for one set of features versus value function for another set of features. And the big open problem, in my view, is now to identify a representation in terms of subgroups of variable that still interpretable, but tells us not only whether a cooperation plays a role, but also which features are involved. And maybe next time I can tell you more about this. These are the references, and I think I'm quite good in time, so we have some more time for questions. Thank you.